everyone who joined us in this session. Welcome and thanks for coming. As usual in my courses, first of all, I have a very small and brief review to the previous session. In the last session, I defined Banach algebras and say several examples of Banach algebras, and some of them were unital and some not. For example, maybe Banach algebra has an identity, but its subalgebra maybe it doesn't have identity. Like, for example, C0 of X at the subalgebra of CB of X, of course, for non-compact locally convex space. And also, for example, K of X as a subalgebra of B of X, I mean the space of compact operators, and this is the bounded linear operators. And we know that it is unital identity operator, but it is unital just when dimension X is finite dimension. Otherwise, it's not unital because the identity operator is not compact. Oh, another example, for example, the algebra of continuously differentiable functions, Cn, and the Lipschitz algebras. And also this algebra, I don't know if I mentioned its name or not, but anyway, it consists of all, it's the algebra of all continuous functions and the unit disk in the complex plane, which are analytic on the interior of a D. And we know that this is a disk, and we call it a disk algebra. I don't know if I yesterday mentioned it or not. It's better to take my notes. And this is a closed subalgebra of C of X. And then I say that because always a non-unital Banach algebra can be embedded in a unital Banach algebra. So in the rest, we consider our Banach algebras, all of them are unital. And the last thing I mentioned was the character and character space of A. Character space of A, it means that the set of all functionals from A to C, B is a character. It means that phi is non-zero linear functional which preserve multiplication. In other words, non-zero homomorphism. And just a small proposition. For example, each character at E is 1, and for each non-invertible, any invertible element, sorry, phi of A is not 0. It was the last thing I told you yesterday. Now I want to continue with characters and some important results in spectral theory of Banach algebras. The first theorem I want to tell you, which it's really important, and I give it a star in place when I told you, remember that theorem, I mean that this star theorem. Of course, we have another one, we have it later, but anyway, this star theorem, I give it a star. It means that it says that if A in A and a norm of E is less than 1, then E minus A is invertible. And inverse is with inverse this summation an and from 0 to infinity. Of course, it maybe doesn't make sense for each A, but for such A in Banach algebra is meaningful. And for proof, uh, since norm of an and from 0 to infinity, it is most sigma of norm of an because of submultiplicity of the norm and subadditivity, of course. And we know that this is a convergent series. Actually, it's a geometric series in R, and because the norm of A is less than is strictly less than 1, so it's convergent. And since A is a Banach algebra, so this summation is meaningful, and we have this is convergent in A. So because of this, there exists B in A such that B is the summation of n from 0 to infinity. And of course, here A is compact. I mentioned, but I prefer also to write it. Okay. So we have this element in our algebra, and now we want to show that this is inverse of E minus A. E minus A is summation of, for example, an, and from n to m, we have summation of an, and from 0 to m, minus a n, and from 1 to m plus 1. And so with this relation, finally we get just the first sentence here and the last term here. Means that E minus a m plus 1. But when m goes to infinity, this goes to E because an goes to 0 because of convergent, and also finally because of continuity of the multiplication, we can say that n from 0 to infinity is E. And from the left also similarly, summation of an and from 0 to infinity multiplied by E minus A is E. Then this is inverse of E minus A. Then B is the inverse of E minus A. This is very useful theorem in our proofs. So it's better to remember it for next parts. Anyway, okay. We obtain a very nice corollary from this theorem, and I prefer to tell this result here. The first one, it says that if P in M of A and A in A with norm of E is less than 1, then absolute value of phi of A is at most 1. And the second part says that if phi in M of A, then phi is automatically continuous, and the norm of phi, the operator norm I mean, is 1. So it's very nice result because it shows that you know that the character is just a algebraic concept. When we can, for example, we define character without any topological structure. But with this with this just algebraic concept, but we can obtain that this is automatically continuous when A is a Banach algebra. It doesn't matter commutative or non-commutative. Of course, for commutative, there is another way to obtain this result easier. But anyway, this theorem is correct for all Banach algebras. This very nice result. Okay, for proof, the first part, we know that we say that if lambda is a scalar, the absolute value of lambda is strictly greater than 1. We don't, it cannot be phi of A. So if lambda is a scalar greater than 1, then norm of lambda inverse A, which is lambda inverse norm of A, is less than 1. Of course, we can say that not only less than, because it doesn't matter, because again, here it's less than 1. We can, it's okay, it's correct, of course, but even we can say that it's strictly less than 1, because there's no problem if we put equality here, and then anyway, it's important to have strictly less than 1, and we have it because norm of A is strictly less than 1. And then, and so by the previous theorem, E minus lambda inverse A is invertible. And so, so since it's invertible, and as I mentioned here, we have invertible element cannot be 0. We have this element is not 0. And phi is linear. It says that, and phi of E is 1. So it says that we have lambda inverse phi of A. In other words, phi of A is not lambda. Hence, the absolute value of phi of A is less than 1. And for the second part, we want to say that the operator norm of phi is 1. We know that the operator norm is the supremum of absolute value of f of phi of A, their scalar. When norm of A, it doesn't matter. We consider supremum all those elements in the closed unit ball, the interior unit ball, and just unity sphere. I told even yesterday. Anyway, and this is, and since phi of A E is 1, and then norm of phi is 1. And it's automatic continuous, and automatic continuous with norm 1, of course. Now, next up, I want to define a very important concept in spectral theory of Banach algebras, which is a spectrum. And what's the definition of spectrum? The spectrum of A in A, which is denoted by this notation, sigma of small sigma of A, is defined like this: is the set of all lambda in C such that lambda E minus A is not invertible. And some books, they use spectrum of A. It's also very common notation. I'm sure that you've seen such a definition before in your algebra. Of course, as you see, this spectrum is completely an algebraic concept because it doesn't matter if A is just a unital algebra, we can have this definition, but for main results, of course, we need to have Banach algebra, some of them just features of Banach algebras. That's why we have to consider Banach algebras. Anyway, you've seen such definition before. Um, for example, let A is Mn of C, and A is a matrix in A. A spectrum of A, according to this definition, is lambda in C such that lambda identity matrix minus A is not invertible. So when a matrix is not invertible, because we are in finite dimensional, so it's equivalent to this fact. This one as an operator is not injective. So it means that there exists X non-zero vector in Cn such that lambda minus A at X is 0. In other words, it means that AX is lambda X. And you know that such a scalar is called eigenvalue for matrix A. So for a matrix, the spectrum is just the set of eigenvalues of A. Okay. So, before saying more definitions, more examples, sorry, because I just say one definition, which is to somehow familiar with you, because you've seen it's a matrix algebra as a set of eigenvalues of matrix. The first thing, before saying more examples, I think the first fact with respect to spectrum, which is this remark. I think maybe you've seen it before for matrices. Anyway, if A and B in A and E minus AB is invertible, for example, with C as the inverse of this. For simplicity, we put it C, for example. Then E minus BA is also invertible. And the inverse is E minus BA. Inverse is E plus BCA. Of course, it's really easy to check because, for example, E minus BE multiplied by E plus BCA, we have E minus, for example, BA, and this one minus BA, BCA. and this one B, C, A. And for example, take out B from here and CA from here. And we have B, A, B, and from this, when we vector B and CA, we have C, no, sorry, just E, CA. Okay, I put it, I think, plus B minus AB. Yes, it's true. And we know that this is inverse of this element, so it is E, and finally it is just BA, and finally we get E. From the left also, it's easy to check that it's inverse of these elements. Then we can say that a spectrum of AB minus 0 is equal to a spectrum of BA minus 0. This is a remark I wanted to mention. Just really nice remark. Anyway, then let's go some examples. Apart from matrix algebra. For example, let A is C of X and F in C of X. According to the definition of a spectrum, it means that the spectrum of F, it means that lambda in C, such that lambda identity element or unit element, it means that it's the constant function 1 minus F is not invertible in C of X. But you know that when we have a function which is continuous, 1 over F is also continuous. If the zeroth set of F is empty, I mean that F never vanishes on X. If it's not invertible, it means that zero set is not empty, and so there exists, it shows that there exists X in X, such that lambda minus F at X is 0. In other words, it says that lambda is F of X. So when lambda is here, lambda is F is X, small x. Lambda is the range of F. And we can go back. If lambda is the range of F, we can go back and see that lambda minus F at X is 0. I mean that's the zero set of function. Zero set, I mean that X in X such that F of X is 0. This is a zero set of function. The zero set is not empty, and so finally the function is not invertible. So spectrum of F is just the range of F. And exactly similar for Cn. Okay. I can write here, of course. It's older. For Cn, you know that when F is n times differentiable and n's derivative is continuous, 1 over F is also have a similar situation. If again the zero set is empty, I mean that the function never vanishes on I. And we have formula for the inverse of function. Anyway, so as another example, when A is Cn of I and F in A, again, we have a spectrum of F is F of I, the range of F. It's also similar for A when it's Lipschitz algebra and F in A. Exactly here, the same situation like here for C of X or for Cn of A, because if G in leap of X and the zero set of G, I mean that the set of X in X such that G of X is 0 is empty, so G never vanishes on X, then G is also a, sorry, 1 over G is also a Lipschitz function, because it's really easy, because for each different points like X and 1 over G at X minus 1 over G at Y, we have just G of, for example, Y minus G of X, G of X, G of Y. But we know that G is not 0 for each X, so absolute value of G of X is greater than 0. And X is compact metric space, so the minimum also is of course minimum, it will be in the range of G, and so minimum is positive scalar. So M as the minimum of absolute value of G is positive. It's strictly greater than 0. So sorry, I forgot to, anyway. Because of this relation, we can say that it's finally 1 over M2, and this is G of X minus G of Y over D of X and Y. Then this is L of G over M2, which is finite. So 1 over G is also Lipschitz, but because L of 1 over G is finite. And so because of this theorem, again, this exercise is a exercise, we can say that spectrum of F, again, F of X. And for example, when A is CB of X and F in A, but we aren't allowed to have, like here, we aren't allowed to have 0 in the range of F, but here, because it is not necessarily compact, we aren't allowed to have 0 in the closure of the range. So it means that here, the spectrum of F, it's easy to see that is the closure of F of X is closure in C. Okay, sorry. Yeah. You know, the main object here is to show that spectrum of A is non-empty and also a compact subset of C. The compactness is not that much difficult, but to show that spectrum is non-empty, it needs a little much work. But anyway, it's a nice achievement in the theory of Banach algebras, and we mention it here. Okay. There's no special chats. Anyway, comment. It's okay. We continue. Okay, but before saying the next theorem, I just fix a notation. If E, for example, if E is a normal space, Then um, ball of uh, A around A and sorry, let's introduce A, E, and R positive. Then ball of A and R, it means that the ball around A and radius is R. It means that B in E such that norm of A minus B is less than R. And of course, the closure, when we have closure here, we have here less than or equal to R. The closed ball, we have also equation here, apart from inequality. Anyway, or neighborhood, maybe sometimes some books says neighborhood of A and of radius is R. Anyway, uh, in the next theorem, we show that the set of invertible elements of each Banach algebra is open subset of A. A inverse is an open subset of A, and the second part says that the map, the inverse map, the map A to A inverse to A, which takes A to A inverse, is differentiable. So, okay. So change it. Okay. And when we want to show that if, for example, a set is open, we can show that each point is an interior point of the set. So let's A is in inverse of A. So I try to find a suitable ball around A, which is completely inside A inverse. In other words, I try to find a suitable radius. If B is sufficiently close to A, then B will be invertible. The suitable radius can be 1 over norm of A inverse. If B in A and norm of B minus A, so yes, it's 1 over A inverse, then we can say that norm of E minus, it's like I want to take out A inverse from right, and so because of submultiplicity of the norm, norm of A inverse, I prefer to write it in the right side, norm of A minus B, norm of A inverse. This less than 1 over norm of this guy, so it's finally less than 1. And so, because of a star theorem, E minus this element is invertible. E minus this element would be B A inverse. So B A inverse is invertible. And A inverse is a group. A also is invertible. So finally we get B is also invertible. So We can say that ball of A and the norm, for example, the radius like this, which is a suitable radius, is completely in A inverse. So A is an interior point of A inverse, and it works for each A. And then A inverse is an open subset of A. And now we want to show that the second part, A to A inverse, is also differentiable. Write it here. Um, to show the function from A inverse to A inverse function is, for example, differentiable at A in A inverse, we need to define a linear map like L from A to A such that the limits, the definition of course, the definition of derivative, but in Banach spaces in norm of this function, I want to show that it is differentiable. So it means that f of A plus h, so A plus h inverse f of A, and f prime of h, so this is L of h over norm of h is 0. We define this linear map as follows. Define L from A to A by conjugation by A inverse and sign minus. By L of B is minus A inverse B A inverse. Conjugation of A inverse and minus sign. I want to find a suitable bond for the numerator of this fraction and then use it to show that this fraction goes to 0 when h goes to 0. If h in A with norm of h less than 1 to norm of A inverse, then norm of A inverse h, it at most 1 over 2, and in particular less than 1. So according to Star theorem, E minus this element is invertible. Of course, because I need here E plus A, so I write plus, but it doesn't matter because norm of E, this element and it's minus this element, the same. And so, because of Star theorem, E plus A inverse H is invertible, and we know that the inverse with inverse this summation. A inverse H power n from 0 to infinity. Now I want to calculate this one. Let's take out A inverse. So we have norm of E plus A inverse H is like this. Imagine A inverse is take out minus E and plus A inverse H. If we put this element here, and of course, we miss the first and the second term here. And finally, we have sigma from n from 2 to infinity A inverse H power n. And according to submultiplicativity of the norm and subadditivity, of course, we have norm of A inverse H power n and from 2 to infinity. We know that this is a geometric series, so this would be A inverse H power 2, 1 minus norm of A inverse H. But we know that norm of H, this is less than 1 over 2, minus is greater than 1, minus 1 over 2, and 1 is greater than 1 over 2. When we consider converse, and so finally we get is 2 norm of A inverse. And let's use again to submultiplicativity, and finally we can like here. And now we can calculate this limit because we have everything, of course. This is just this, but it seems that A inverse is taken out, and I think everything is ready to have the last calculation. Okay. Okay, limit of this element, norm of A plus H inverse minus A inverse plus A inverse H A inverse over norm of H, and this is like E plus A inverse H inverse A inverse, and from this calculation here, and use submultiplicativity of the norm, we can write norm of E plus A inverse H inverse minus A inverse plus A inverse H norm of A inverse over norm of H. This is, if you remember, this is 2 norm of A inverse power 2 H power 2. And because of this, we can put like this, and we miss H and the power, just 1 H, and it goes to 0 when H goes to infinity. H also goes to 0. And this completes the proof. The proof is complete. Okay, inverse is differentiable function. Now, as a conclusion of this theorem, we can at least say that a spectrum is a compact subset of complex plane because it's closed and also bounded. So if A in A, then a spectrum is compact, and also we can say that spectrum is a subset of a closed ball around zero origin and reduce the norm of A, the closed ball of this. It means that for each lambda, the absolute value of lambda is its most norm of A. Okay, first it's easy theorem result. Of course, it is not that's much hard to prove it. First, I show that it's sorry. But it works well. I don't know. Hope it works well. At first, we show that this is bounded. This is bounded. I mean that we show that if the absolute value of lambda is strictly greater than norm of A, it cannot be in the spectrum of A. So if absolute value of lambda is sorry, then norm of lambda inverse A because of this is less than 1. And so because of star theorem, E minus lambda inverse A is invertible. When it's invertible, lambda E minus A is also invertible because it's not 0. So it means that lambda is not in the spectrum of A. So we get spectrum is a subset of ball of 0 reduce A, the closure, of course. And now it's easy to show that it's compared. For example, you can take a sequence, convergent sequence in spectrum and show that the limit point is also in spectrum. And for example, I want to show that it's closed. And let's lambda n be a sequence in a spectrum of A such that lambda n goes to lambda in C. I want to show that lambda is in the spectrum. When because of the continuous operations, we have A, doesn't matter, of course. Lambda n E minus A goes to lambda E minus A. Lambda n is in a spectrum, so lambda n E minus A cannot be invertible. So this is in A minus A inverse. A inverse is open, so A minus A inverse is closed, and then lambda E minus A is also here. It means that it's not invertible, and so lambda is not is in a spectrum because this is not invertible. Another way, which is really maybe it's even easier and simpler, for it's not easier, for it's of course is easy. Anyway, you can, for example, function like g from C to A, it takes lambda to lambda A minus A. This continues, and G inverse of inversible element is exactly C minus spectrum of A. Is open, G is continuous, so it's open. This one is open, and finally, spectrum is compact. Anyway, spectrum is compact. Yeah, sorry, spectrum is closed and then compact. Because of Heine-Borel theorem is closed. And finally, we can get spectrum is closed, is compact, sorry. Now we reach to our main result here, which I want to say that spectrum is non-empty. But before saying that, let us recall some information from function analysis. You know that A star, the dual space of A, is the set of all functions from A to C such that phi is linear and continuous or bounded bounded with operator norm and with ASR, what we can start topology, which is a locally convex space as a topological vector space. And we can start topology, I mean that the weak topology in use by A, or A topology of X. A topology of A star is called weak star topology. And actually, this topology, for example, a net phi alpha in A star, and for example, phi in A star, phi alpha goes to phi in weak star topology. It means that for each A, phi alpha A goes to phi of A for each A in A. And it's very important topology, and especially for function algebras, Banach function algebras, we need many times this topology, A star, of course. Anyway, for this, okay, but the thing I wanted to tell you, A star separate the points of X, the points of A, I mean that if A and B are distinct points in A, we can find a linear functional here such that phi of A is not equal to phi of B. So A star separates the points of A. Oh, now we have our theorem. If A in A, then the spectrum of A is always non-empty. Of course, if A is 0, then 0 as a scalar is in spectrum of A because the 0 is not invertible. That's why spectrum is not empty. So we assume that A is not 0. And to prove this, and to obtain a contradiction, we assume that spectrum is empty. So to obtain a contradiction, suppose that spectrum is empty and define this map and define the map like this from C to A inverse, which takes lambda to A minus lambda E inverse. Uh, of course, because spectrum is empty, for each lambda, this element is invertible, so it's well defined. I want to show that this function is bounded. If absolute value of lambda is greater than 2 norm of A, then a norm of lambda inverse A is less than 1 over 2, and in particular strictly less than 1. So according to the star theorem, E minus lambda inverse A is invertible. And the norm of E minus lambda inverse A inverse, exactly this element, minus E. We know that this is because I don't have enough space, prefer to use at least this one. It's sigma lambda inverse A power n, and from 0 to infinity. So E is omitted, and so finally we get this summation from 1. And again, multiplicative property of the norm, and we get this geometric series, which is convergent because norm of A lambda inverse norm A is strictly less than 1. And the norm and the summation is this. And again, it's less than 1 over 2, minus is bigger than 1 over 2, and 1 minus this is bigger than 1 over 2, and then converse. Finally, we get is 2, even strictly 2 norm of lambda and A. And this is also less than 1, less than 1 over 2, and finally we get 1 here. Okay. Anyway, now we can say that this function is bounded outside the ball around 0, and the radius is 1 over, sorry, radius is 2 norm of A. So this boundary is this is this function exactly, just E, because we can use a triangle inequality, and finally we can say that norm of this element is strictly even less than 2. So norm of E is 2. Then norm of E minus lambda inverse A, yes, A inverse, I think, uh, yes, it at most 2. Okay. I think okay. No, no problem. But it's a little different, but there is no problem. Um, but just like here, there is no any problem. We can say that norm of A minus lambda inverse is actually, we can write here lambda inverse, um, lambda inverse A minus E, and also here we can say, let's write it here, lambda inverse, norm of lambda inverse A minus E. This is less than 2, and this one is, but here we know that the absolute value of lambda is greater than this one, and so inverse would be 1 over 2 norm of A, and finally 1 over norm of A. So then norm of A minus lambda E inverse is less than 1 norm of A when absolute value of lambda is greater than or 2 norm of A. So outside this closed ball around 0 and radius is then 2 norm of A, this is bounded. And on this closed ball, it doesn't matter because there is no any problem here because this function is continuous and the ball is compact, and so we have boundedness. Also, this map is continuous on the compact set ball around 0, and the norm is 2 norm of A. So it is bounded. So the function is bounded over C. This function is bounded, and also this is differentiable because inverse is differentiable. So it's easy because we, in one of our previous theorem, we saw that this is differentiable, A to A inverse, and it's not difficult to see that this is differentiable. And it's bounded over C, so it's an entire function. And when we have an entire function which is bounded, maybe you've seen it in complex analysis, such a function must be constant. Anyway, so I write more details. Um, then there exists M such that norm of A minus lambda inverse is at most M. Then I want to use the Liouville theorem, but Liouville theorem, because it's from C to C, that's why I apply elements in a dual space here. It's here. If phi in A star, then the map from C to C, which takes lambda. Let's phi apply to this element, phi of A lambda inverse is bounded. The bound is, for example, we can consider norm of phi m, because phi of this element, absolute value of this, is at most norm of phi, norm of this element, and from this is bounded, for example, by norm of phi and m multiple by m, and it is differentiable because it's A to A inverse is differentiable, and of course, because the whole complex plane, we can say that it's entire. Now we can use Liouville theorem in complex analysis to say that this function must be constant. Okay, let's recall the function from here. It was phi of A minus lambda inverse is constant. Okay. So by Liouville theorem in complex analysis, this map is constant. Then for each p in A star, this is constant for each p. For example, put lambda 0 and we have phi of A inverse, and if lambda is 1, we have phi of A minus E inverse. And therefore, for each p in A star, we have phi of A inverse, if I don't know, it's equal to phi of A minus E inverse. But you know that A star separate the point, and then we get A inverse is equal to A minus E inverse. And so we get A is equal to A minus E, which is impossible. And we get a contradiction. It shows that the spectrum is non-empty. This very important result in the spectral theory of Banach algebras because I told you it's just feature of Banach algebras. And so it's very important. And for example, if I point out some, at least one of most important results in this area, I can point out Gelfand major theorem, which characterizes all Banach algebras, which are division algebras. And of course, they showed that this algebra is just the complex plane, the complex field, nothing more. And this is very nice exam. It's very nice theorem. And we get it from the non-emptiness of spectrum. Gelfand major theorem. Uh, let me write it completely with complete details because it's a famous theorem, and I want to, if you have a look, you just see the whole theorem. If A is a unital Banach algebra, which is division algebra, it means that in which every non-zero element is invertible, such that A inverse is the whole A minus 0, then A is just C. A is isometrically isomorphic to complex plane. And the proof is not that much difficult, of course, with the aid of the previous theorem. Okay, let's A in A. Since spectrum is non-empty, there exists lambda in C such that lambda in a spectrum and then let's see here. So according to the definition of spectrum, it means that lambda E minus A is not invertible. Any element expect just 0 is invertible. So should be 0. Lambda E minus A is 0. In other words, A is lambda E. So it's clear the map which takes E to 1 from A to C is an isometric isomorphism. Okay. Then the map from A to C, which takes E to 1 in C, is an isometric isomorphism. Isometric, I mean that norm of each element here is the norm of element here. It's clear because, for example, A takes 2 lambda E, and we know that norm of A is the norm of lambda E, because here we have this equation. And isomorphism, it means that it's linear and bijection and also preserve multiplication. So the only division algebra, which is Banach algebra, is C. And the last thing I want to tell about spectral theory is the definition of spectral radius. Sorry. Okay. The last thing I want to tell you is spectral radius. The spectral radius of A in A, which is denoted by usually by R of A, is defined like this. Is R of A is defined by supremum of absolute value of lambda when lambda in the spectrum of A. We are not worried about this. We don't worry about it because we know that spectrum is non-empty and compact, and so this is bounded. And anyway, we have these facts. The first one is R of A, which is, of course, a non-negative scalar, always is at most norm of A. Because you know that we proved that spectrum of A is subset of lambda when it's norm of A, which is the ball of the closure of this ball. We just saw it before. And the second part, we can say that R of AB is equal to R of BA for each A and B in A, because the spectrum of AB minus 0 is equal to a spectrum of BA minus 0. So we have this one. And we have a nice formula for spectral radius, and I would like to mention here. Okay, let's write it here, of course, statement. Before saying this theorem, just say some examples. For example, when A is f of x, c of x, sorry, and f in A, we know that the spectrum of f is the f of x. So the spectral radius of f is the supremum of elements here. It's just subnorm of f. So sometimes we have exactly the equation. But for example, let A and 2 of C and A like this. Norm of these elements is 1, and the only eigenvalue is 0. It's easy to check. So R of A is 0. So we have exactly inequality. Or for example, let A C1 of I and F in A. We know that spectrum of F, for example, F is, let F is identity function. The spectrum of F is F of I, and which is I. And so R of F is supremum norm here, is 1. But you know that norm of F is supremum norm of F plus supremum norm of F prime, which is 1. Again, here we have strict inequality. Okay. Now, let me mention the nice formula for spectral radius. Okay, and also from this theorem, we can obtain the first part of remark, but anyway, it's better to use that theorem because I want to apply this, the first part of remark here to this theorem. And the theorem. If A in A, then a spectral radius of A is the infimum of sequence norm of an power 1 over n, which is also limit of this sequence. Of course, this sequence is convergent. And this limit is norm of, sorry, R of A. If lambda in a spectrum of A, then for each n, natural number n, lambda in a spectrum of an. No, because lambda n E minus an, we can write like E minus A, and lambda and if lambda n is not in a spectrum, it means that this element is an invertible. But if it's invertible, this will be invertible. Maybe you think that the right inverse and the left inverse, it may be different, but no, it's easy to say, to check that it will be invertible. They are the same. Anyway, so when it's invertible, these two guys are invertible, especially this one is invertible and lambda cannot be in a spectrum. And then, according to this remark, absolute value of lambda n is at most norm of an, and um, and it works for each n. And so absolute value of lambda is at most the infimum of this sequence. So it works for each lambda in a spectrum. So for supremum, we can say that supremum is the spectral radius. We just like it here. And so the spectrum, the spectral radius is at most infimum of norm of an power 1 over n, which is, of course, we know that this is at most the inf of norm of an because we don't know if it's convergent or not. So let's put it, for example, 1 here, and then I use it to obtain the equation. Actually, it remains to show that lim sup of this sequence is at least norm of, sorry, R of A, spectral radius of A. Okay, for the converse, let delta be like this. Ball of around 0 and radius is 1 over R of A if R of A is not 0. And otherwise, if it's 0, put C. Of course, they're the same. We can, for example, with identification of 1 over 0 is infinity, we can just write ball of 0, 1 over R of A. Doesn't matter. write it here. If lambda in delta, then E minus lambda A is invertible. It's clear because when lambda is here, it means that absolute value of lambda is less than 1 over norm of f. It means that lambda inverse is greater than R of A. So such a square cannot be in a spectrum. So it means that E minus lambda inverse is invertible. And so this is invertible because lambda is not 0. I mean that's clear. Anyway. Let's P and A star, the Euler space of A, and we know that the map from like F from delta to C, which takes lambda to phi of these elements. Phi of E minus lambda A inverse. Because A to A inverse is differentiable, so this is differentiable and delta is an open set, so we can say that it is analytic. And as I told you, when a map is analytic, it's the uniform limit of polynomials. And so there exists sequence like Cn in C such that f of lambda is Cn lambda n from 0 to infinity is the uniform limit of polynomials. Okay. And lambda, we know that lambda is just for emphasize lambda in delta. I want to determine this coefficient Cn. If absolute value of lambda is less than 1 norm of A, which is of course is less than 1 over R of A, then we have norm of A lambda or lambda A is less than 1. And so according to star theorem, and E minus lambda A is invertible. And the inverse element is, of course, let's say just write the inverse element and not mention that it's invertible. Anyway, this is lambda A n from 0 to infinity. So compare these two relations. Just if we apply phi here, we just have f of lambda. So, and hence we get phi of f of lambda is phi of this element, and phi is linear and continuous, and so we can get phi of an lambda n. And now compare these two relations. Of course, when lambda is here, lambda is in delta, and so there is no matter. We can compare this, and with comparison, we can obtain that Cn is phi of an. Therefore, we obtain this one and this one, and then Cn is phi of An. And just write f of lambda phi of An lambda n, and from 0 to infinity for each lambda in delta. In particular, it shows that it's a convergent series, so it goes to 0 at infinity, and especially its bounded sequence for each p in A star and lambda in delta. Uh, since P of An lambda n goes to 0 for each lambda in delta, it is a bounded sequence for each lambda. And from this argument, we can say that for each phi and for each lambda in delta, phi in A star, the dual space of A, phi of An lambda n is bounded. And then we can use the uniform boundedness principle and say that An lambda n should be a bounded sequence. Let's write it. From the above, Ban lambda n is a bounded sequence for each phi in A star and lambda in delta. If we fix lambda, then we can use the principle of uniform boundedness. We can say that this, without phi, of course, this is bounded for each lambda. So by the principle of uniform boundedness, f An lambda n, um, lambda n An is bounded for each lambda in delta. So for each lambda, there exists m lambda such that we have this bound for this sequence, norm of lambda n. An is at most, for example, m lambda for each n. And then for each lambda in delta, we, we write it an m lambda and 1 over n, just omitted here, 1 over n. And so norm of an is lambda inverse m lambda 1. Because I want to divide by absolute value of lambda, let's lambda is not 0. And then let's have a limit and two-sided and n. So we don't know if it's convergent or not, but I can write lim sup or lim if, but here I need lim sup. So I write lim sup. It's independent of n, and this one, the limit is 1. Lambda in delta, and have a look to delta, this ball. So we can write very close to boundary, and we can let lambda inverse go to, or lambda goes to 1 over R of A, and lambda inverse goes to R of A. We get a lim sup of norm of an power 1 over n, it at most R of A. And then finally, we have lim sup of norm of an is at most R of A. On the other hand, lim sup is lim inf of norm of an. Always we have it for each sequence. And from 1, the relation 1, we have infimum of norm of an power 1 over n. And this is, sorry. And so R of A is infimum of norm of an power 1 over n, and this is limit of this sequence. This is a nice formula for a spectral radius. And for example, from this theorem, you can, for example, like calculate this one and see that, for example, norm of Fn. Fn here is xn, and norm of Fn is 1 plus supreme norm of F prime, which is n, and this is goes to 1, and we can get R of F. Okay. This was the final thing I want to tell about the spectral theory of whole Banach algebras, commutative or non-commutative. But in the rest, I concentrate on commutative Banach algebras, and I attempt to cover the Gelfand theory. And the mainly reference here is functional analysis rule. If you want to follow, you can see more this book. Anyway, so Um, we consider commutative Banach algebras in the rest. Always in the rest, algebras are commutative. Just one case. One algebra is not necessarily commutative, but I emphasize that time, and I mentioned that it's not necessarily commutative. But anyway, apart from that case, the other parts, algebras, all of Banach algebras are commutative. So I don't mention specifically, for example, a commutative Banach algebra. Uh, Here, I want to bring the definition of ideals. I know that you've seen this definition in your algebra, but anyway, I want to use them, and so I prefer to bring it here. Okay. A subalgebra I of A is called ideal of A if is subalgebra, so we have this if AB is in A for all A in A and B in I. The ideal of A is called proper if I is not equal to A. And the last part, uh, the ideal of A, the ideal I of the ideal of A, it doesn't necessary to introduce the I, is maximal ideal if, sorry, I have I, if I is proper, if it's proper and not contained in any larger proper ideal of A. So the maximal ideals are proper, and also they not properly contained in any proper ideal of A. And trivial ideals, from the definition, we can say that 0 and A itself are proper, and sorry, so are trivial ideals of A. I want to say a very small proposition, which is really easy to prove, but let's write it here. Proper ideals cannot have any invertible element. It's clear, because otherwise they will be the whole algebra. Anyway, if A is a proper ideal of A, then intersection of A, I'm sorry, A inverse and I is empty. And the second one, which is also, it's also easy, if I is an ideal of A, its closure, of course, the same. So is It's closure. It's closure. So it's an ideal of A. So it's closure. It's really easy to prove the first one because if they have intersection I and A inverse, so because of the property of ideal, the unit element should be there, and then each element in A will be in I, but it's not possible because I is proper. And the second one also, it's easy to check that closure of I is an ideal. Because we introduce I here, let's here introduce the notation, write the notation. Okay, the first part is easy. The second part, of course, is easy, but let's write it. For example, if let's A be in closure of A and C in A and lambda in C. Because A is the closure of A, so there exists a sequence like AN goes to in AN goes to A, and sequence like BN goes to B, and then because of the continuity of operations, lambda AN plus BN goes to lambda A plus B, and also CAN, for example, goes to CA. Ideal, so in ideal, and finally lambda A plus B and CA, all of them in the closure of A, I. And the next theorem also is not difficult to check that. This theorem, I'm going to don't over the time, don't be over the time anyway. Theorem. I think the first part you've seen again in your algebra. Every proper ideal of A is contained in a maximal ideal of A and the second one, the maximal ideals are closed. For example, because I want to introduce them to summarize to somehow anyway. Each proper ideal of A is contained, this is I. We use it with Zorlem, of course. We consider the subcollection of all ideals, proper ideals, which contains I, and using Zorlem to obtain the maximal ideal of A. Let's sketch a proof, say sketch a proof anyway. I put B be the collection of all proper ideals of A which contains I, which is partially ordered by set inclusion. Uh, Actually, there's a lemma states that if we have a partially ordered set and each chain here there has the upper bound, then we have at least one maximal totally ordered subset of this set. And so here, because it's partially ordered, but if we can consider a chain, I mean a totally sub collection of P, and we consider the union of this chain. Of course, this is ideal because of we have totally ordered, and also this proper because all of them are proper, and E is not belong to any of them, and so it cannot be in the union. And of course, all of them contain I, and the union is the same. So each subcollection has an upper bound, and we have, so by Zornemo, we have a totally ordered subcollection of P. By Zornemo, we have a totally subcollection of P, like totally ordered subcollection like L, for example, or Q, or maybe. By Zornemann, there exists a totally ordered, a maximal totally ordered subcollection. A maximal totally ordered subcollection like Q of P. And let's M be the union of elements in this subcollection, which are ideals in Q. So, as I told you before, for chain, M is ideal and is proper. And because this is maximal subcollection, this is maximal ideal. Then M is the maximal ideal of A, contains I. Say right, why, but say, just say it orally. Just 5 minutes. Okay. Okay, let's see the second part and finish this session. Um, According to by the preposition we just speak for, M, closure of M, is an ideal of A. And and M is the subset of closure and it's in A, but this is proper actually because E is not in M. Otherwise, if E in the closure of M, we know that A is invertible element and this is open. And according to the definition of closure, then if, so otherwise if, then A inverse and M should be have some intersection, non-empty intersection. So then A inverse intersection of M is non-empty, which is impossible, again, because of the previous proposition. And then M is maximaloidal. Then M should be equal to closure of M. Okay. I have to just stop here. And anyway, I finished the session now. And many thanks for coming. And I hope to see you everybody next session. Have a nice day. Bye.